Assalamu alaikum wa rahmatullahi wa barakatuh. I am Haytham Raid Ibrahim. Best regards to our great lecturer Dr. Ja'far, and also my respect to my classmates. First of all, I would like to thank you for giving me this opportunity to explain my topic and present it, which is the decision tree under the machine learning. I hope that I will be able to explain it well, and I hope it will be easy for understanding. So I will start my presentation from the agenda. So my agenda will include, of course, an introduction for the topic of decision tree, and also I will explain more details about the decision tree, and also the divide and conquer strategy, which is the most important strategy for decision tree, will be presented. And also during this presentation, the differences between univariate and multivariate trees will be a part of my presentation. In addition, more details about a binary tree will be explained in details. And also the entropy and impurity, which are another important topics, will be explained during this presentation. And also the regression and classification trees will be a part of this presentation. And also the importance of base split, which is a very important term during the structure of generating the decision tree. So during this presentation will be explained. And also the pruning trees in the end of the structure of decision tree, the importance of that will be presented. The idea of role extractions from the trees, and also learning rules, and finally the rule inductions. So first of all, it's important to know that the information revolution around the world made a significant change to the life of people. And we know the root for this change is the technology or the technologies. So this is the most important part during the information revolution. And when we are talking to the technologies, we have to mention to the fact that a good data allows organizations to establish baselines and achieve their goals to keep moving forward. So our aim is to achieve our goal using a good data. And it's good to know that our goals could be achieved by using another very important strategy, which is as known around the world, data mining. So data mining refers to a process to extract usable data from what? From large set of any raw data, and that depend on the intelligent technologies. So again, we refer to intelligent technologies, which is very important to get the benefit of our data, and by using it we can get a very important data. And also when we are talking about the intelligent technologies, it is fair to mention that the most popular tool used for data mining is a decision tree, which can describe a dataset by a tree-like structure. So the structure will be like this. So the decision tree is a hierarchical data structure, and also it is a supervised learning. And again, it is a hierarchical data structure and supervised learning. And during this strategy, the local region is identified in a sequence of recursive split using a strategy of divide and conquer, which is very important strategy. So we use this strategy, divide and conquer, for simplifying the complexity of problems. And this strategy is widely used for this purpose. So in general, our topic is talking about the problem, how the problem is difficult, and how we can simplify this problem by dividing it for sub-problems. And in case if we see that the sub-problems also are difficult, so we can divide them, each sub-problem for sub-problems. And then we can get the solutions after solving these problems or sub-problems. During the conquer step, we can combine the solutions to get the final solution for our problem. So we will explain more details about decision tree. So in order to understand the strategy of divide and conquer, we will explain this pseudocode. First, we have this problem. First, we check if our problem is small or large. So if our problem is small, so just solve the problem. Else, here we have to divide the problem for sub-problems. Sub-problem 1, 2, and so on. Then we divide the principles of divide and conquer by solving sub-problem 1 and sub-problem 2, and so on. And then we have to combine the solutions that we collected from applying the divide and conquer to get the final result. Then in next slides we will discuss how the learning algorithms build tree from training data, and also how the tree can be converted to a set of simple rules. Specifically, how to convert it for if-then rules, because it's easy and simple for understanding. Now moving to univariate trees, we can say that in each internal node, the test uses only one of the input dimensions. So we take only one dimension. And we can explain that by using this example. So let's say we have these attributes of color. So here each node, node 1, node 2, node 3, each node corresponds to one of the three possible values. So we have three attributes, red and blue and green. So each one just corresponds for only one value. So for univariate tree, we will explain this example on this figure. So consider that we have this case of classification. So to classify, to get better split or classification, we can split this figure for more than one split. So this is the first decision, which is the root decision that includes the whole set of data. We take the first decision when x1 is bigger than w10. This is w10, and if more, we have to talk about this part, and if no, then we are talking about this part. So this is the split will be from here. If no, so we have only blue shapes, circle shapes, and if yes, we just go for the next condition, this internal node. So if x2 is bigger than w20, this is w20, we will make another split here to get more pure split. So we will get these leaves, this first leaf and this one, and this is also another leaf node. So these leaf nodes refers to final result of classification. And here we have to mention that for univariate trees, that many studies have concluded that the univariate trees are quite accurate and interpretable. So moving to the multivariate trees, on the opposite of univariate trees, the multivariate trees, here all input dimensions can be used, and thus it's more general, so it is able to use more than one condition step in only one node. Multivariate trees are more complex and hardly justified. At the same time, it's more powerful learning algorithm. So this is an example we can see here in this figure, how we just use one supplet and we can get from this supplet a very pure classification. So in one decision node we used more than one condition. Actually we just put all conditions and get the leaf node early. So regarding to multivariate trees, here that means we have more decisions in one step and reduce the steps of the supplet. So we have to know that in general the decision trees composed of root node and internal node and also leaf nodes. So 3 levels of nodes. So for root node, we can see that all data records are placed in this node. So the root node includes all data records that give it a more generalization, and we can apply for each node, for root node and internal nodes, a function, we call it fm function, except the leaf node level. We cannot apply this function for leaf node. And just we go ahead and the tree grows down by splitting recursively data at each level into new node until leaf node, until we reach the leaf nodes. And by reaching the leaf node, that means we just hit our goal for the decision tree, and by recursively splitting the nodes. And again, when the root node has the all data records, so all nodes has a subset of this data. These are the leaf nodes, which refers to the terminal level. Another definition for decision tree is an efficient method used for both classification and regression. We can see here, this is the figure for classification, how the instances fall near to the supplet line, and here for regression also how the data or instances fall near to the supplet line. So we continue suppleting recursively until a leaf node is created and labeled. After we get the leaf node, the output label defines localized region in the input space. So for the input space for both of classification and regression, we get the localized regions, and for the classification, the localized region or label definition is the class code. So the instances for classification fall near to the class or class code. For regression also, the data or numeric data label helps data or instances to fall near to the this data. Here also we have to say that the supplet in decision tree will be better with maximum separate power. So the maximum separate power could be achieved by a good decision. So the decision lead us to go and get the best split. The binary tree, for the binary tree in the best case, each decision element or eliminate half of the cases. In binary tree, each node has at most 2 children, no more than 2 children. So we explain it for the binary tree by this figure. This is the figure of binary tree, and we can see here this is the root node, how the root node has only 2 children, and each internal node has 2 children only, until we reach the last level for leaves. And we can see here the binary tree called strict or proper tree, because it's easy for understanding, and it's strict by splitting the data and instances in half. Also we can see this is the root node, consider in level 0, and other levels will start from L1, level 1, and so on until last level. We can also know how many nodes we have in any level. So I mean, for complete binary tree, we can know how many nodes we have in complete binary tree in any level. So what is the complete binary tree? All levels except the last level has 2 children, and it's full, and the maximum number of nodes at any level, or which when we take the level I, will be 2 empowered by I. So for level 1, we can say the number of nodes will be 2 empowered by 1 will be 2. For the next level 2, we can say that in this level 2 we have 4, because level 2 empowered by 2 will be 4 nodes. For last one, because we don't have complete tree, or not all nodes has 2 children, so we cannot assume how many nodes we have in this level. So until here we need more explanation for decision tree, the whole idea, and based on that we will explain an example, and from this example we will get the knowledge for the rest of the decision tree. Let's assume these data belongs to a tennis player, and the data refers to how the tennis player will play or not based on the weather situation. So we have the outlook, temperature and humidity, wind, and the final decision for a player, if play or not. So no refers to not played, and yes refers to played. So first of all, we have to make a discussion related to this example. We can see here we have this figure refers to how the player has 50% of data played and 50% not played. So we have a high impurity here, and we can say here if node M is not pure. So we start from root node, and we say if this node is not pure, so we have to split, then the instances should be split to decrease the impurity. We have to decrease this impurity, and starting from the fact that learning is greedy to find the best split recursively, and then we check if the subset after the split are closer to pure, then a fewer splits will be needed, if any. If the subset after split is not close, we have to make more for splitting, and we will see how we make this. And in condition, if the subset is pure, full pure, so no need for any more split. Of course, this refers to locally optimal, and that may prevent us to get the smallest decision tree. Actually, in this topic we focus on how to get the smallest decision tree, and we will see why it's important. And knowing that the finding of the smallest tree is NP-complete problem or NP problem. So it's a difficult problem where no efficient solution algorithm has been found. We have to try to get this smallest decision tree. Again, we have no choice but use local search procedure based on heuristics that give reasonable trees in reasonable time. Going back to our example, we see here for question 1 and question 2, we assume the data is 16, not 14, like the question, just to explain it very well. We have in question 1, we have these data 4 times not played and 6 times played. And for the other side, the no refers to 4 times played and 2 times not played. So we can say, just for looking for question 1, we have for both of sides for this question, we have a high impurity because we don't have any pure data refers to the player played or not played. For question 2, we can see it's more likely to be pure, so less impurity. So if node M is pure, we have to generate a leaf and stop splitting. Otherwise, we have to continue recursively split and continue find the best leaf for this condition. For the other questions, question 3 and question 4, we can see here for question 3, less impurity we have in this question, because we can see if yes he played, for no he not played. Clearly we can say that. For question 4 also we have to make more split to get the decision. But first of all we have to know how we get the best split. We can make split, but how we get the best split? Actually, from looking for this example, we can just see there is a high impurity when we go up for the root node, and lower impurity when we go on for the other levels for the decision tree. I mean for internal node reaching to the leaf nodes. Regarding to the situation of impurity, we can calculate the purity of the split or the impurity. So the impurity could be calculated by finding the probability and log of probability for both of positive and negative situation. For positive situation, we mean the player is played, so the decision is yes. And for positive or negative, for negative situation, we just focus on how the player will not play. So minus p plus we have in question 3 8 and log for probability plus minus probability for negative situation. We have also for question 3 8 times, so 8, and log for this probability. Here we can see clearly how we apply this equation. So minus 8 for 8, log 2 for this probability also, and minus 0 for 8 because 0 times didn't play in this decision node. We can see 8 times he played actually and 0 not played, and also we take the log for this probability. So the result will be 0 impurity, so we have a pure decision for this decision node. So again we say here in classification tree the goodness of a supplet is quantified by what? By an impurity measure. So for classification tree, it's important to have the impurity measure. And clearly we can see a supplet is pure if after the supplet, for all branches, all the instances choosing a branch belong to the same class. When the instances go ahead for the same class, we can say here our supplet is pure. I mean low impurity. And also for all types of attributes, for discrete and numeric. I mean for discrete classification and numeric for regression. For all supplet positions, we calculate the impurity and choose the one that has the minimum impurity. And based on that, the tree construction continues recursively until we get all of them are pure. And regarding to the size of tree, actually we can get a very large tree, and that will take us for another problem, which is overfitting, that may affect on the performance of test data. Because when we are starting our testing data, these instances may will exploit our training data or training results, so that will take the instances to fall in unlikely or unpreferred situation or data. So basically we have the situation of overfitting when the error in our training data is low and the error in our testing data is high. On the opposite, we have the underfitting. So we get the underfitting when the error for our training data is high and the error for our testing data is low. The best situation for fitting is the generalized model, when we have a low error for both of training data and testing data. And actually we can reverse for the training data errors by bias, and for the errors for testing data is variance. So by measuring the impurity for first question, we point the result on this chart and continue for the next question, and we can see here we have one time of the player not played. So we have 7 for 8 probability of playing, and we take the log for this number also because it refers to the positive situation for playing. And also we have the log of 1 divided by 8, which refers to the player didn't play. So the impurity will be here 0.54. And for the next question, we have also this probability refers to 5 times the player played and 3 times the player didn't play. So we have to take this positive and negative data and find the impurity for that, which is 0.95. For the other situation, we have 4 times played, 4 times didn't play. So we have 1 entropy or impurity by calculating the probability for that and the log based on the equation. For the rest of questions, we can see that the data will make a curve from 0 to 0 and reach the level 1 in the middle. I mean when the impurity will be 1. So on the other side, we have the opposite situation for the first situations, and the impurity will go down again, and we can see here how the impurity will be reduced again and again until we reach the final situation when we'll go back again for 0. I mean for opposite or the negative situation when the player didn't play. So when the player played or not played, I mean he made the decision or a pure decision, we have the impurity 0. And for confusing situation or impurity situation, we have high impurity, which reach to 1. So until here, our data refers to two probabilities, which is played or not played. But in situation of, we have more than two probabilities. I mean, for if we change the data referring to if the player played on Sunday, Monday, Tuesday, Wednesday. So if we take this probability or the situation when the player have 4 probabilities, how to get the entropy for that? So in this situation, our equation will be like this. Rather than we have P positive and P negative, now we will have Pi. And the value for this I actually reach until K. And in this example is just 4 because it includes 4 probabilities or 4 classes. So assume we have the P1 refers to the red color and P2 refers to green color, and blue color has a P3 and yellow color has the probability or class for P4. So P1 refers to the probability of red color, which is 1 of 10, and also the log of 1 of 10, which is actually minus, multiplied by the minus probability of green color, which is 3 to 10, log 3 to 10, multiplied by the minus probability of blue color, 2 for 10, multiplied by the log of 2 of 10, and so on for the yellow color also. So now let's go back for our example and let's count the entropy for both of the set and subset for each question. For question 1, we can see that we started from entropy 1 and ended with the entropy reached to 1 for the yes, which is 0.97, and for no situation we got the entropy 0.92. So we still confused based on this entropy, and we didn't get a benefit from these results because we started from 1 and ended with values near to 1. So we didn't get a big difference between the set and subset. While for question 2, we started from entropy 1, but for the subsets we got a new values. So we gained for this question a big data that refers to the pure decision. For first part, we moved from 1 to 0, and the other side is 0.72, which is at least better than the values of question 1. So the idea is how to collect the entropy for the set and subset, and each question of these 4 questions, each one has the highest purity will be the better. But at the same time we have another problem. When we have very less data for the subsets, that will lead for high variance and make a generalization error. Actually, we cannot say that this player will not play based on one recorded data. So it's possible we have 0 impurity, but at the same time we have very less recorded data. And especially when we compare between 2 parts of decision node or 2 questions, it's not fair if we say the player will not play based on 1 record data. So the solution for this situation is by counting the gain or information gain by using this equation. So to calculate the gain of set S of question Q will equal the entropy of set S. So in example, we want to calculate the gain for the question 1. We go for the entropy for set 1, I mean for the root node. So the entropy will be, in our example, is 1, minus the summation of the entropy for the subsets for question 1, I mean for yes probability and for no. So the probability for situation yes for question 1 is the 10 of 16 multiplied by the entropy of this situation or this root node, which is 0.97, and so on for the other side for the situation no. So let us calculate it by going for our example. The information gain for set S of question 1 equals the entropy of set S, which is 1 from the original set, minus the probability of the set 1, I mean for yes probability, which is 10 of 16, multiplied by the entropy of this subset, and so on for the other side of this set, which is the subset no. So the final result of the information gain for question 1 will be 0.049. For question 2, we will make the same steps and we will get the final information gain will be 0.55. And we can see here that the information gain works on the opposite of the entropy. In case of entropy, we saw that when the entropy will go less, so that will be better for our decision tree or for the purity of decision. But for the information gain, when the value will be larger, so that will be better. So the information gain for question 2 is better than question 1, and that could be seen clearly. For question 2, we can make a pure decision better than for question 1. So let's apply this equation for our original question, and here we have 14 instances for the probability related to the wind. When the wind is weak or strong, we have 2 subsets. So when the wind is weak, we see that the player 3 times played and 3 times didn't play. I mean 50% of the data is played and not played. And here we need to make a calculation or split to get the decision. Here we calculate the impurity or the entropy for set the first set and also for the subsets of this set. And we can see here clearly for the weak winds, we can see the entropy is 1, and this is the worst result we can get and confuse us and cannot make a decision. And by calculating the information gain for that, we will get the final result will be 0.048. Here we will repeat the process of this equation for other questions. So for the question of humidity, we will get information gain 0.151, and we can see here this result is higher than the previous one. And also for the question of the temperature, we can see here we have 3 subsets: hot and mild and cool. So here we will calculate the entropy at first for the subsets, these 3 subsets, and then we calculate the information gain for this set. The result will be 0.042. And until now we can see that the best result, which for the set of humidity, that is 0.151. For the last set, we have the outlook. Also, we have three subsets: rain and overcast and sunny. We calculate first of all the entropy for each subset, and we have the entropy for the set previously. And by calculating the information gain, we can get the result, which is 0.247, which is the highest value from the 4 questions. And that basically refers to the better result until now. And here for the subsets, rainy and sunny, we can see until here we didn't get a high impurity, or we didn't get a pure decision. Here we can repeat the same process for information gain and calculate it for these subsets until we reach for the pure decision tree, and we can see the overcast here already pure and get 0 impurity, so no need to split it again. And after calculating the information gain for all sets and subsets, we finally get this shape. From this shape we can assume if the player will play or not play in the future based on this tree. And from this data and from this decision tree, we can actually assume if the player will play or not, and at the same time we can know how the player thinking. So this is why we are working on this decision tree belong to machine learning, because basically it's just like the way that the human thinking. So we can interpret the decisions of the decision tree. We can see here for the sunny day, and we can play when the weather is or outlook is sunny with normal humidity. And for the rainy also, we can play when it wind, and also the wind is weak and not strong. Another benefit from this decision tree, we can actually see that the temperature doesn't affect on this decision tree. So we don't have temperature records, and we can conclude that the temperature will not affect on the data or the decision of playing tennis. The decision tree can help us to neglect the not important data or not important attributes. So basically we can recognize between the rich data and not important data based on this information that we got from decision tree. And also we can predict an event based on the decision tree. So now we will talk about another important topic related to decision. Now we are talking about another topic related to decision tree. Actually it's an important topic that is pruning trees. Previously we mentioned that the problem of overfitting may affect on the testing data. So as we see here in this figure, we have this tree and we have many subsets of this set or this internal node reaching to the leaf node. So the idea of pruning testing is just removing the subtrees for better generalization. I mean early stopping. As we mentioned in previous example, when we said it's not fair for generalizing a decision based on very few recording data or testing data. So here we need to generate the smallest tree to get a better generalization for decision tree, because we want to make sure that we will not fall in overfitting problem as we mentioned. and it is possible that this decision tree can help us to make a feature extraction to use it in another decision. So for this tree, we can stop earlier to prevent falling in the overfitting, and that could be achieved by using even pre-pruning or post-pruning. For pre-pruning, we can stop tree construction earlier before it becomes full. So basically, we can stop this split if a number of training instances smaller than a certain percentage of the training set, let's say less than the training set in 5% only. So we here work regardless the impurity or errors. Just when we reach to the 5% or less or any other percentage that we will adjust, before we set or reach this percentage, we can stop pruning or splitting this decision tree. But the question here, why we need to prune this tree? Actually, any decision tree based on too few instances, as we mentioned in our example before. So this causes variance and also causes a generalization error. So we set a pruning set, we replace pruning node with leaf node. The other pruning type is post-pruning. Actually, in this type, we just grow the whole tree, then prune the subtrees which overfit, or we see that these data are not important or doesn't make sense for decision tree. We can just prune these data and then stop splitting this decision tree. And when we compare between these two types, we can see that the pre-pruning is faster than the post-pruning, and the post-pruning is more accurate. Why? Because in pre-pruning we just save our time, and in post-pruning we need to generate the whole tree and then we decide to stop splitting. On the other hand, in post-pruning, in practice, works better than pre-pruning, because we see how the tree growing and continue further on until all leaves are pure. After that, we try to prune unnecessary subtrees. In the other meaning, we can say that we grow the tree full and we have no training error. So then we find the subtrees that cause overfitting and we prune them. After pruning, we are going now to talk about the rule extraction from trees. We have in this example this decision tree which is deal with the numbers. These include decisions start from the root decision, which talk about age that bigger than 38.5. With this type of examples, I mean the examples or decision tree that deal with numbers, the better algorithm used is C4.5 rules. So this is an important algorithm used for this type of data. So in order to extract our rules in decision tree, we must know that decision tree make own features extractions, and we can see here the type of rules is just if then rules, which is easy for understanding and explanation. And when we are talking about the univariate tree, we must know that univariate tree only uses the necessary variables, and after building the tree, a certain features may not be used at all. We can prune it. At the same time, we can also say that The features that are closer to the root node, are more important and globally because it has the whole set of data. So for this example, we can see that x1, x2, and x4 used in the figure of this example. But when we are talking for x3, actually we didn't use it for this decision tree. So for feature instructions, we build the tree and then we take only these features that used by the tree as input for another tree. So we make it a feature instructions for a learning method. And the rules can be written basically in a figure or in a shape of if-then rules, and we can call it a rule-based. And these rules reflect the main characteristics of the dataset. They show the important features and split positions. So our rules, if-then rules, allows knowledge extractions, and that can allow experts to verify the model learning from data. And also we have to say that the pruning could be possible for simplification the rules. We can split the rules also. And for learning rules, it is important to know that rule induction works similar to tree induction, except that the rule induction does depth first, search, and then generate one path, one rule at a time, where tree induction goes depth first and generate all paths. And related to generating rules, we have to talk about the sequential covering, which is the process of generating rules one at a time until all positive examples are covered. Once a rule is grown and pruned, because we said that rules also could be pruned, it is added to the rule base. So we make a rule base, and after a rule grow and pruned, we add it for this base, and then we can remove all training tests when all training examples covered by the rule, and the process continue until enough rules are added. So in order to train a decision tree, we can do it by getting if-then rule. Actually, the rule is constructed from conjunction of conditions on discrete or numeric attributes. So refers to classification and regression. And again, we are talking about adding a rule. We must know that we could add the rule by covering outer loop, which add one rule at a time to the rule base. Also, an inner loop of adding one condition at a time to the current rule could be achieved. So the rules or the process of adding rule or condition to the rule is a greedy process, and both of them can have steps for pruning to get better generalization. For rule induction algorithm, rules are added to explain positive examples. If an instance is not covered by any rule, so that will make it classified as a negative. So for covered will be positive and not covered will be negative. So let us say we have rule R, and R bar is the candidate rule after adding a condition. So after adding a condition, the R will be R bar. So the change in gain is defined as in this equation, gain of R bar from R equals S of log 2 for M bar plus and M bar. When M bar and M bar plus are similarly defined for R bar, for added decision for the rule. And S is the number of true positive in R. And also it's still true positive in R bar. And that after adding the condition. And also N refers to instances that covered by R, and N plus without bar is the number of true positive in them. For N instances covered by R. So in machine learning, we have the rules, and we can extract this rule from the observation of the sets of data or instances. And that could be represented in a full scientific model of data or a pattern. In more explanation for tree induction, we can say that the tree induction is nothing just the construction of the tree given in a training sample. And actually we are interested to find the smallest tree from the given training sets, which exist in many trees that coded with no error. Here we have explanation of pruning the role of set rule for positive and negative. So each rule belongs to a set of rules. So here we have DL and DL bar. So if DL bar is less than DL, after adding the condition, so here we have to delete rule from rule set and return to the rule set. And then we optimize the rule set, for rule set positive and negative. For each rule belong to rule set. If DL0 or DL1, replace rule for rule set positive and negative. And also in reverse order, if DL1 equals many of DL0, DL1 and DL2, we have to delete rule from rule set also, and add replace rule for rule set positive and negative. Else, if DL2 is minimum or min DL0, DL1, DL2, also we have to delete rule from rule set and add reverse rule for rule set, rule and positive, negative, and also return the rule set. So in the end of the presentation of the topic of decision tree, we will explain some advantages of decision tree, are the feature extractions, and the possible to use the decision tree for feature extraction and build a tree and then take one of the features used by the tree as input to another learning method. Another advantage of the decision tree is the interpretable ability for decision tree, because we are using easy decisions statements of if then. So the decision node carry conditions that are simple to understand. The tree can be converted to a set of if then rule, also called rule based, that are easily understandable. And also each path from the root to the leaf corresponds to one conjunction of tests, as all those conditions should be satisfied to reach to the leaf. For this reason, decision trees are very popular and sometimes preferred over more accurate but less interpretable methods, because of the ability of interpretability for decision tree. And also the process of top-down induction of decision tree, we can refer to it for TDIDT, is an example of greedy feature for decision tree and for the algorithm. and it is by far the most common strategy for learning decision tree from data. Finally, I want to refer for the C4.5 algorithm for decision tree, which can be deal with numeric data, and it's not strict for the records if we forgot to record any record of data, and it's not continuous. On the opposite of that, we have the ID3 algorithm, which deals with the discrete data. So until here, I have finished the presentation of the topic decision tree belongs to machine learning. I hope that the presentation is clear and the whole idea of decision tree is pure. Thank you very much for concentrating with me and watching this presentation, and best regards. Now we are talking about another topic related to decision tree,